Hello there, and welcome to the grad school of the Symposium on Geometry Processing 2020. My name is Marco Couturi, and this will be a 90 minutes lecture on computational optimal transport. So the first question that I would like to ask is, why optimal transport? Well, the first thing you should notice is that this is a field that is drawing the interest of very different people. People in very different fields such as economics, applied and pure maths, graphics, and also machine learning. And this is very exciting because it seems that everybody in those fields finds a common ground and a common interest for the same set of ideas. And the field of applications of optimal transport is getting broader and broader. And for instance, it's exciting to see that in recent weeks or months, we have seen very interesting results pop up in biology. So another reason why this is a very interesting field is that it has a bit of everything. Whether you're someone very interested in theory or in algorithms, applications, optimization, statistics, probability, numerical analysis, etc. And this is probably why this is a field that is very lively and that seems to benefit a lot from these different disciplines interaction. And so the field is usually attributed to a mathematician from France, Gaspard Monge, in the 18th century, who basically tried to answer a very concrete problem, and in doing so started with exciting theoretical ideas. Although he really deserves the credit for launching the field. For about 150 years, the problem was so hard to solve that it wasn't really studied. And we had to wait for a long time until Kantorovich and other people got interested in it again, right around World War II. And for their work on this topic, Kantorovich and Koopmans, an American economist, Dutch-American economist, got the Nobel Prize in '75, Nobel Prize in economics. An important figure in that field was also George Dantzig, who was the first to propose a numerical algorithm to solve the optimal transport problem that Kantorovich and Koopmans had worked on. For many years, optimal transport stayed in the world of optimization and operations research, essentially as a logistics tool, until a new generation of mathematicians got interested in it in the 80s and 90s. And those are the works of, for instance, McCann, Otto, Brognier, Caffarelli, and Gangbo, who not only generalized much of what had been studied by Monge, but also for the first time were able to prove some results and to study even some numerical aspects of this problem. And then later there was a second revolution, I would say, in the early 2000s, with the work of Ambrosio Villani and Figali and many others, that extended this toolbox of optimal transport to study actually other problems in mathematics. And Villani and Figali respectively got the Nobel Prize in the Fields Medal, 2010 and 2018 for their work. So if you want to look at, for instance, trends, well, there seems to be a trend. Here I've plotted the curve of search interest for Wasserstein metric, which is another word under which optimal transport is known. But if you just look at the number of submissions in major machine learning conferences, you will notice that by the year there is an increase in the number of papers that cite, that use optimal transport, Wasserstein, or Sinkhorn in their title. So it's a thriving domain right now, which is finding new applications. So before I actually get to describe this theory in detail, I would like to give it an informal definition. And the definition might be that it's a very natural geometry for probability measures. And this is, this is SGP, well, of course this matters, right? Probability distributions are found across every type of application. And so defining a new geometry to study them has a lot of impact in terms of what algorithms you can do, what algorithms can do to study those data types. So The first example we can consider here is that of statistical models. After all, statistics is really the discipline that is concerned with estimating, comparing probability distributions. And so most of statistics is built on the Kullback-Leibler divergence. And so if you actually change the geometry and start using the optimal transport geometry, then you have a lot of impact and a lot of things to rethink. The reason it's also now used in biology is that in many cases in biology, when we look at cells, we only have access to populations of cells. So this is what you would see, for instance, in a petri dish. And typically, because it's very hard to measure and keep track of one single cell across time, what is done is that a population of cells is given. Half of them are taken to take measurements, because when you measure something on a cell, you typically kill it. So for that might be, for instance, gene expression profiles. And then you let the other half continue on its own and develop and duplicate, etc. And time after time, what you get access to is a probability distribution of cell features. And so it's been used a lot, optimal transfer has been used a lot to keep track of that evolution. In NLP, it's very common to represent paragraphs of text or an entire text as word clouds. And that is basically the text itself without its structure. It's just the vocabulary that is used in the text. And usually because some words appear more frequently, they have some weight. So this is what this H1 and H2 here in the middle of the slide represent. And so recently optimal transfer has been used to compare two such word clouds. In neuroimaging, you might see the brain activation on the cortex of a patient as a map, taking values on this cortex. And if you normalize it appropriately, you might come up with a positive measure on the cortex, or even a probability measure on the cortex. And so in that setting, you might want to compare those two activations. In the generative models literature recently, which has grown a lot in importance in recent years in machine learning, one wants to compare the manifold of the generated data that's given to you, by a generator algorithm. That would be a generative deep neural network, and the data that you are given. So for instance, on the left, we have a space of code words, which have very low dimension. There is a mapping that takes you from those code words to the space of images. And to train GANs, typically what you want is that the manifold of generated images that you have here in the middle in red is close to the probability distribution on images that you can sample from the internet, for instance. And so being able to compare those two here is important. Having a good geometry to do so is important. Finally, in graphics or image processing, of course, we have a lot of probability distribution, descriptors that can be cast as probability distributions. So here that might be the color palette of two images. So in each of those cases, optimal transfer has shown new ways to handle those comparisons. And one of the important things to notice is that really optimal transfer is very geometric. It is essentially something that will look at a pair of observations that will start from the geometry on the space of observations to define meta-geometry on the space of probability distributions supported on those observations. So the basic paradigm in optimal transport is that if you give me a way to compute the distance between two words, any pair of words, so this would be public and car here, I can give you a way to compute a distance between probability distributions on words. If you give me a way to compute the distance between two areas in the cortex, then I can provide you with a distance on two activations. And the same thing goes for colors, for instance. So all of this basically makes optimal transfer a very intuitive tool, a very intuitive geometric tool, but one has to remember that it is one that builds on an important a priori knowledge, which is a geometry on the space of distributions to produce a new geometry, a meta-geometry. Now, so this was the GAN example. So what I would try to cover in 90 minutes is basically 1, 2, and 3. An introduction with intuitive ideas and math, and then distinguish two regimes. One where optimal transport can be computed exactly, and one where it's actually more beneficial to use a different approach to compute it. And this is what I call computing optimal transport for data sciences, and that essentially relies on using regularization. I will leave in the slides some selected applications, but I will not have the time to cover them. So in the introduction, I will describe two fundamental problems that have a historical meaning, because those were the ones that were considered at the time, and explain basically what is the intuition behind those two optimal transport problems. And although they are related, they are different enough that they deserve a different spot for each other. Once this is done, I will provide just mathematical definitions, and then we can proceed to computations. So the field starts with Gaspard Monge in 1746. Born in 1746, died in 1818, so a French mathematician that lived through the Revolution. And if you're not from Paris, well, if you were to come to Paris, you will see that a lot of places are named after him. So he had a very big impact on French history. And so, for instance, here's a page about Place Monge in the 5th arrondissement of Paris. There is a Métro Monge as well, a subway station, etc., etc. So what Monge studied in 1781 is the following problem. He basically says, when one has to carry earth from one place to another, there should be a good way to do it. By this, one that minimizes the notion of effort. So here's the example that we will play with. Imagine this is your garden, and you have a pile of earth that is standing there, and you want to fill up a hole that is somewhere else in your garden. And for the sake of simplicity, we'll assume your garden here is just a 1D single dimensional line. And so Monge asks the following question. If I have to use the sand that is on the left, or the earth here on the left, to fill up the hole on the right, what would be an efficient way to do so? So it's pretty obvious that in the 21st century, if you were to ask this to anyone, there's not much thinking or planning that needs to happen. You just bring a machine and just push the entire mass of sand so that it covers the hole. The thing is, in 1781, you have to picture that we didn't have access to such machines, and so the only way to do so was to ask a worker to actually physically go to a location X on this real line, pick up the sand that was available there, and this is an infinitesimal amount of sand. It's just mu of X. It's an abstract column of sand. And what you want the worker to do is to move that sand, right? And what Monge says is we should provide the worker with an instruction on how to move precisely that amount of sand that the worker finds at X, and that is defined as a mapping T. So for every location X where there is sand, T of X will define where the sand should be dropped. And so in doing so, the worker goes from X and brings the sand to T of X and walks a distance of the distance between X to T of X. Now, of course, the further away that point is, the more work is involved. But Monge does not forget the fact that you also need to multiply that distance by the mass. If you have to bring 1 kilo, it's not the same as if you had to bring 2 kilos. And so Monge makes the assumption that the cost or the work here is basically proportional to the distance times the amount of mass, mu of X. Now, the map T that I just introduced cannot be anything. So for instance, if you just introduce a map T that would be such that T of X is equal to X plus 1, that would mean that for every elementary mass at x, you will just shift it by a distance of 1. And then, in that case, you would just recover the red pile of Earth here, just shifted by a unit of 1. And that's not what you want. You want to actually fill up exactly the hole, such that it's exactly flat on the right-hand side. And so how can you ensure that this is true? How can you ensure that the map T, that if you give me a map, is going to satisfy this? Well, the important thing to notice is the following. For every segment that I will be considering, B on the real line, and that is somewhere in the support of nu, there must be some sand coming from the red pile of sand that lands there. And the way to define this mathematically is to write it as T minus 1 of B. So this is an inverse in the set sense. This is just going to be all of the points, locations x, such that my function T of x tells me to put sand in B, to land somewhere in B. And for the purpose of, just to illustrate this, let's suppose that currently the map T is such that it takes all of the sand supported on 3 segments, A1, A2, and A3, and brings it somewhere in B. So the natural conservation of mass constraint here would be that the amount of sand that is going out of those 3 segments is equal to the amount of sand that you need exactly at B. And you can write here in this way, it's the mass of those three intervals according to the measure mu is equal to the mass of the interval B according to measure nu. In other words, you want that for every B, the mass of the inverse set of B under T in the first measure is equal to the mass of the segment B in the second measure, the target measure. And to take a simpler notation that probabilists like, basically this is the same as saying that the push forward of measure mu under the action of T is equal to nu. So if you apply the function T to every infinitesimal amount of mass that is described in measure mu, you will eventually reconstruct exactly the measure nu. So the first problem that appears here is this is a fairly heavy constraint on the map. I'm pretty sure you won't be able to find here a map, for instance, intuitively that is such that it pushes forward the mass of mu to nu exactly. But Morge doesn't really consider that feasibility. He just says, well, I want to consider maps T such that they guarantee this conservation of mass, this push-forward constraint. Imagine there's a few of them. Now, which one is the one that minimizes the total effort? So if I can choose a map T among those that push forward the mass mu to nu, which one involves the least amount of energy or effort? And that is the question that is asked by Morge. Notice that this problem is actually quite hard to solve, and this is why Morge proposed it in 1781, but we had to wait quite a long time before we were able to make numerical progress on this problem, numerical or even theoretical progress. One of the reasons this is a hard problem is that the constraint T push forward mu is equal to nu is not the convex one. Now, there is another problem that is very much related to this one that was proposed 150 years later, which was solved numerically within 10 years. And that is the discrete optimal transport problem, also called the Kantorovich problem. So to be fair, there were quite a few people that studied that problem, and they all discovered it around World War II. And the historical context is interesting. Here, Morge cast his problem as a public works application. All of the authors here cast it as a logistics problem. And logistics was really a crucial weapon in World War II. And this is why so many people tried to develop tools to improve efficiency of logistics. And so it's usually attributed to Kantorovich, but there are other people such as Hitchcock or Tolstoy that also contributed a lot to this problem. So imagine this is World War II, and we are somewhere in Stalingrad, close to Stalingrad, and this is the battle is raging between the Red Army and the German Army. And currently you are a Red Army general, and you must do some planning. And what you have is that you have some soldiers which are in some configuration, they are in their barracks. So there might be, for instance, 60,000 soldiers up on the left, 90,000 up on the right, and 150 in the lower right of the screen. But you want them in a different place right now because you need them to be on the front line. And you want 120 of them to be on the left, 90 in the middle, and 90 in the bottom. So the question that Kantorovich asks is, given a transportation network here, which is indicated using dotted lines, what would be the optimal way to move the troops? What would be a good way to move the troops? Well, without even thinking about optimality, there's one very simple way to solve this problem without thinking too much about the transportation network, and it's the following. What we know is that there are basically, we need 120,000 soldiers on the left, 90 and 90 in the other two locations. Which means that in terms of proportions, we need exactly 4 soldiers for every 3 soldiers that we put in the middle and 3 soldiers that we put in the bottom. This is, the proportions is 4 to 3 to 3. Therefore, a very simple solution would just be to split with those proportions all of the current barracks and then send the troops accordingly. So what you can see is that this basically results in quite a lot of movement because you have not considered a transportation network. The solution that you have provided here has never looked at whether location of the upper left was very far from the front line of the lower right. And so this is somewhat a very naive transportation. However, it makes sense. I mean, it's one which is somewhat maximally robust to issues with the transportation network. Now, what can you do if you really want to take into account the transportation network? What can you do if you want to find a cheaper way to move around all those troops and to reach the target number of soldiers? Well, basically Kantorovich said this problem is easily described using two sets of parameters. The first one is, let's just forget about the entire story and look at what is in the beginning and what is in the end. What we have is 2 histograms that sum to the same quantity because we need exactly the same amount of soldiers that we have available. So 60 plus 90 plus 150 is going to be equal to 300 as well. So on the one hand, we have those histograms, those masses, and on the other hand, the problem is entirely described with the geometry. By geometry, I mean just simply the distance between each barrack here to each of the front lines. So I've called the barracks 1 to 3 and the front lines ABC. I just need to fill up that distance matrix. Now, the problem requires me, as a Red Army general, to say exactly to which barracks, to every barrack, what is the amount of soldiers that they should send to each of the 3 front lines. So I just put 3 question marks there for each barrack, and in total we have 9 question marks. So those histograms, we will call them the marginals, and the distance matrix is basically the cost. Now, if we just make this a little bit more abstract, what we will call those question marks is just simply a variable that is indexed by a barrack on the one hand and the front line on the other hand. And let's just pretend that those numbers actually can be anything, as long as they sum to the same quantity. So Kantorovich says the first thing. Well, first, by a very basic conservation of mass argument, I need that every row in this transportation matrix is equal to the number on the left. That means that the amount of soldiers that I'm going to send to each of the front lines in the row fashion must sum to what is available in that particular barrack. So for every I in 1, 2, 3, the sum on the rows is equal to what is available in the barrack, whereas for every j in ABC, meaning every front line, I will need to get exactly what I want. And this is the conservation of mass argument. And then Kantorovich just simply says, well, the cost of a particular transportation matrix is just going to be, for every pair of barrack and front line, the amount of soldiers that travel there, in between them, times the distance. So this should ring a bell and sound very similar to what we were describing with the Morse problem. And indeed, what Kantorovich proposes is just simply to minimize among all valid transportation matrices that satisfy the conservation of mass constraint, those that have the smallest total cost. So, for instance, in practice, this might be something like splitting the two on the upper left and splitting the 150 on the right to get this total movement. So this would be an optimal transport, and an interesting thing to notice is that here the transportation matrix that is optimal is very sparse, but this is not a surprise. This, we will see, is a result of the fact that we're dealing with linear programs. So to summarize, we have a similar story, but told in two different ways. One involves densities and continuous maps that take mass from one measure to turn it into another measure with this push-forward mechanics. And the other story on the left is basically that of Kantorovich, where we have points in the map that have resources, and you can actually ship them around. And one of the mechanisms to do so is to split the mass. That is, you're going to say, I'm going to send 60 of my 150 soldiers to a point, and the remaining ones are going somewhere else. So the mathematics are a bit different. The idea is the same, and because of this, the Morse problem is more studied by people in mathematics. This is mostly because they are going to assume densities, or they generate probability measures, but not necessarily discrete measures, and this is more the Kantorovich problem. Now let me introduce a third way to interpret the optimal transfer problem. This was used more recently by Alessio Figali. And I think it's a very nice story. Imagine you're looking at a cloud. So a cloud is made of zillion particles. You're just looking at it, and of course you can't discriminate one particle from the other. The particles are not colored. There's no way you can actually distinguish two water molecules in a cloud. But what you know is that the particles are there. And they are in some configuration, some density. Imagine that 5 seconds later, you take another picture of the cloud, and you know exactly what the density of all the points, all of the particles are in that second picture as well. So to summarize, you have one snapshot of a probability distribution, another snapshot of a probability distribution after having changed a little bit, and the question that you ask yourself is, among those particles on the left, what is the most likely movement that enable them to reach the configuration on the right? So I can't distinguish who is who. So those particles are not colored. So I cannot say that, for instance, the particle on the left, actually I have observed it to go to the middle, for instance. This I'm not able to do. What I'm able to do is just look at the probabilistic perspective, just the probability, the densities. And so the question is, what would be a good prior? What might have nature done to move from the configuration on the left to the configuration on the right? And this is what optimal transport tries to guess. Essentially, we believe that nature acts by minimizing some form of cost or energy to go from one configuration to the other, and this is what the optimal transport will be about. So let me give you a very concrete application in biology, since I referenced it in the first slides of the talk. Imagine you have a population of cells that you're monitoring at t equals 0, and so each of the cells has some features. So as I said earlier, this might be gene expression, or you could think about visual features or many others. And imagine that you leave the dish on its own for a few hours and come back 6 hours later. Typically, the gene expression profile of a cell will have changed within that time. So the cells will have changed. However, you know that somewhat the cells on the right, the population of cells on the right, is related to the population of cells on the left. So what you've seen 6 hours later has been caused by what was there on the left. And so you would like to be able to actually look at each cell and say, well, I believe this cell on the right is probably this cell on the left that changed its shape or characteristics. And the way you're going to do this reconstruction of who became what is going to be optimal transport. So mathematically, this might be, on the left, I have a feature representation for my cells. On the right, I have another one in the same space. Or more recently, people are working on different spaces. But let's assume this is the same space. And I am going to simply assume there was an optimal transport between them. And the optimal transport is what is going to give me the key of who became what. So here, the optimal transport is really a working hypothesis. It's something that you believe explains in the best possible way what happened. And so this means that if this point was associated with this point, for instance, then the cell that was on the left, the green one, probably was turned into the other green one on the right. And here I think you should draw some parallels with the counter-overage problem. What the counter-overage problem allows you to do is exactly assign this to that. What the Morse problem does is slightly more complicated and more challenging. It tries to estimate an entire vector field of displacements. So this is why, again, counter-overage is usually easier to solve. Morse is maybe a bit the next step. So let's go a bit into mathematics and describe this more precisely. So suppose you have a space omega and you have a cost structure on omega times omega. This might be a distance or anything else. And you have two probability measures in supported on omega. So the Morse problem in 1781 is to find a map that goes from omega to omega, which minimizes among all maps that displace mu to nu the total cost. Or you could also see this as the average cost according to probability measure mu. Interestingly, as I mentioned earlier, there was no progress on this problem for about 2 centuries. And we had to wait for a series of papers on the 80s, and that by Brognier is the most representative, to find a nice solution to this problem, or at least a nice characterization of the solution of that problem. And here the characterization is actually a beautiful mathematical result. It basically says the following thing. If omega is equal to Rd, so the physical space, or Rd in higher dimensions, the cost is a squared Euclidean distance. So notice that this is a bit different from the Morse setup. In the Morse setup, usually we use the Euclidean distance only, not the square. It turns out this is one of the hardest problems to solve. It's much easier to solve it with square Euclidean distance. And what Brognier proved in 1987 is that if the measures mu and u have some regularity, so here we're just assuming they are absolutely continuous, then the optimal transport, T, that moves mu to nu, must be the gradient of a convex function. So by u convex here, I mean a function that is simply from Rd to R. And of course, mathematically, if a function is defined from Rd to R and differentiable, its gradient is a mapping from Rd to Rd. It takes a vector and outputs a vector. And so this is what the Brognier theorem says, is if you're looking for an optimal transport between two measures that are nicely behaved in the squared Euclidean distance cost, then necessarily it has to be the gradient of a convex function. And more generally, for every convex function and every measure mu, if you displace the measure mu according to the gradient of u, you will get another measure, we'll call it nu. Well, it turns out that doing so, to go from mu to nu, is optimal. It's necessarily optimal. So in other words, again, if you take a measure and displace it along the gradient of a convex function, then you will always do things optimally. You will always be moving mass around optimally. You're never going to do something stupid. And so this is a beautiful result that connects convexity theory and optimal transport. And it goes a bit further than that, because what this result entails is a connection between optimal transport and partial differential equations. So let me explain. I didn't mention this earlier, but for those of you familiar with numerical analysis, the constraint that T sharp mu is equal to nu, if mu and nu are densities, are measures with densities P and Q, is actually a very well-known formula, which is a change of variable formulas. This can be ensured by simply stating that if T sharp mu is equal to nu and T is differentiable, then T must be such that the density of an input, the input measure P of x, is equal to the density at the output, at the map point T of x, Q of T of x, scaled by the determinant of the Jacobian of T. Now, if you fit the fact that T must be the gradient of a convex function if T is optimal, this means that for an optimal transport problem, an optimal transport map to be optimal, so let's say that the gradient u here, I'm calling my convex function u f, well, it's the same thing as finding a convex function f such that the formula above is observed, and this is simply stated because the Jacobian of T here, because T is the gradient of f, the Jacobian of T is just a Hessian of f. It's just simply that the Hessian of f is equal to P of x divided by the density of Q at the nabla and the gradient of f at x. So this is the Monge-Ampère equation, and this is what basically brings up a very fascinating link between optimal transport and PDEs. The Monge problem is very important in the pure mathematical world, as well as the applied math world. It is increasingly important in applications because it provides you with a very rich information, which is not only where mass goes where, it's also the map that you can actually estimate on any other point. But the reason why it was not really developed and rather the Kantorovich approach was studied is that if you think about it, this problem is very degenerate. Imagine that the input measure, for instance, is 1 Dirac mass, meaning just mass of 1 at one point. Then you cannot get out of that Dirac mass something else than a Dirac mass if you're using the Monge formalism. Essentially, if you're just taking a shovel and bringing that mass that you found at delta x at T of x, you will just get a delta T of x. And which is why the Kantorovich problem should be seen as a relaxation of the Monge problem. So, in other words, the Monge problem looks for a map that goes from omega to omega, whereas the Kantorovich problem looks for probabilistic maps. Something where when you take the mass at x, you're allowed to spread around the mass, not only at one point in particular, but maybe in different locations. So you could, for instance, phrase it as, for every point x, I am going to specify a conditional distribution, which will be p of y knowing x equals x, and y is going to be this variable that tells me where I can put the sum of the amount of sand that I found at x. And if you just glue together all those conditional distributions, you will get a coupling. And a coupling is a joint distribution, a distribution on the set omega times itself, such that it has all of the right marginals that you want. So, in other words, for every set A and B in omega, the marginal of the coupling according to the second variable on that set A would be mu of A, and the marginal would be nu of B. Let me just picture this in a simple setup. We are in the case where omega is equal to R. Hence, P, if I just follow the definition above, will be a probability distribution on the set R square on the plane. And what I'm essentially asking is that a P, a joint distribution on this plane, is such that if I push all of the mass in one axis, I will get one distribution. If I just push again all of the mass in the other axis, I will get the other distribution. And here you can see that this is obviously what's going on. And if you look a bit at this picture, you will see that the coupling that I've computed here is just simply the product of the two marginal distributions. Basically, Pxy here is just simply equal to mu of x times mu of y. So no matter what measures you're dealing with, even if they are discontinuous, discrete, or whatever, there will always be a coupling that satisfies this, the marginal constraints, because it will be given to you simply by the product of the two marginals. However, in most cases, there will be not only one coupling that exists, but many of them. So here is another example for this particular choice of mu and u. So the most problem, you remember, was finding a map that had this crazy constraint that it really needed to map exactly the mass, bring the mass exactly from mu to nu. And among those constraint maps, find the one that was the cheapest. The Kantorovich problem is much easier. It just says, whenever I have two measures, mu and u, I can instantiate the space of couplings that have marginals mu and u. And I know that there is always such a coupling. Now find the one among those that has the lowest cost, and here the cost is simply the integral of the cos xy to p dx dy. So this is just a linear objective if you want. It's just an integration against p. So c is given to you, it's the cost. The only thing that you need to actually find is p, is the probability distribution, the joint probability distribution. So once you solve this, there's many things that actually you can say about the solution to this optimal transport problem, the Kantorovich one. In particular, it's well known that if the cost c is a distance, or even the distance to power p, then this quantity at the bottom will be a distance that people will call the Wasserstein distance. And this is what what people in the community refer to when they mention the Wasserstein distance. It's essentially a way to measure how far two probability distributions are. But interestingly, and this is what I had highlighted in the beginning, when you give me a new way to compute distances, you can also give me a new way to interpolate between things. So here, the McCann interpolation is essentially the series of very small displacements such that the differences in distance between each of those two things here results in the total distance between mu and u. So that's a very interesting point. And if you start thinking about what is, for instance, this interpolation between 1D distributions, you start seeing very interesting phenomena appear. So on the left-hand side, I've just pictured the interpolation between two measures, two densities, the blue and the red. So the blue is a single-peaked Gaussian, the red is a bimodal Gaussian. And I'm asking, how can I actually mix those two things? You can imagine, for instance, those are two measurements of temperature somewhere, and you want to know, if you have two sensors in the same room, how you can actually merge them. Well, the naive way of doing so with the Euclidean distance would simply be to take those two densities, divide them by 2, and sum them up. And this is what you get with this three-waved density. On the other hand, optimal transport will ask, if I can go from the left density to the right density using this Wasserstein geometry, what happens if I stop in the middle? And this is this mixture that you get here in the middle. You can, of course, start playing with this idea in higher dimensions, as long as you can actually compute the Wasserstein distance and even compute the geodesics in Wasserstein distance. But this we showed was possible in a couple of years ago in a SIGGRAPH paper with Justin Solomon and co-authors. And then we were quite surprised to see that with such a weak geometric formalism as that of optimal transport, which only assumes distance between here voxels, we can actually get interesting interpolations. In this case, or for instance in this case, this was computed by my colleague Gabriel Perret. And so this is to illustrate the fact that the geometry that you get is very, very different from, of course, that of the Kullback-Leibler divergence. And to close a bit this math introduction, let me just say that essentially, up to 2010, in the data science community, in the computer graphics community, a lot of the interest was in trying to compute the optimal transport distance between whatever, point clouds, color histograms, etc. Or maybe to bound it in a quick way. Since around 2010, there's been an outpouring of problems that now are far more challenging and more interesting, which directly try to handle optimal transport as something that you want to minimize or play with. You can compute geodesics, you can try to compute some sort of form of gradient in this Wasserstein space of probability distributions. And those are the problems that we are the most interested in now. We're no longer at the stage where computing the distance is interesting. We're at the stage where differentiating it is interesting. And for this, we can rely on the works of mathematicians that paved the way 2 decades ago. Now, I'm going to explain briefly how and when optimal transport is easy to compute exactly. The first remark that you can make about computing this is that, at least in theory, at least in the definitions that I have provided of the Kantorovich distance, you can actually play in any regime that you like. Couplings are very flexible. There's always going to be a coupling between two things, between two measures. And so if you're just minimizing over the space of couplings, this is always a well-defined problem. And if you're just integrating against the cost, then it's going to be, at least on paper, a problem that was well formulated. Therefore, you can very easily compare two discrete measures, one discrete and a continuous one, and a continuous against a continuous distribution. Now, that doesn't mean that those problems are equally easy. The upper left problem is arguably the one that we can handle the most efficiently. And we will see that this requires using network flow solvers. The right one, the semi-discrete problem, has seen a lot of activity in recent years, a lot of algorithms, and mostly due to Quentin-Mérigot and co-authors. And there's also a trend of using, and this works in low dimensions, so something that is relevant to graphics, and I will point also to tutorials by Bruno Levy on this topic. When you're starting to enter a regime where, because of dimension, you can't actually parameterize your continuous density anymore, you can only sample from it, then you need to use, of course, stochastic optimization. Finally, if you're really in the continuous to continuous setting and you want to compute that, this will only work in very low dimensions, and the method of choice to do so is the so-called Bonamou-Brognier approach. I'm going to focus essentially on either the discrete to discrete setup or continuous to continuous setups when the measures are actually easy to apprehend. And the most notable example for this is univariate measures. So in just one sentence, it's easy in closed form to compute optimal transport, to solve optimal transport between univariate densities, as long as you're using a cost that is well behaved. And so here in this slide, I'm presenting the results for a cost between 2 points. That is a convex function. I'm overloading a bit C here. It's going to be the convex function of the difference between x and y. So wherever you are on the real line, bringing mass somewhere else only depends on how far that is. We are not going to be location specific, it's just going to be translation invariant. And if that cost is convex, optimal transport is essentially about quantile functions of the distributions. It essentially says, if you're computing optimal transport between two densities, just look at their quantile functions and then integrate the difference in those quantile functions. So if all of this sounds a bit abstract, look at the bottom. We have two distributions that are supported between 0 and 10. We first compute their CDFs, so that's the integration of those densities. And what you can see here is that the left measure, of course, took values much earlier on the left, between 0 and 5, whereas the right measure took values after 5. And so the CDF starts shooting up immediately for mu, whereas it is a bit slow in the beginning and goes up for nu. Now, to go from those CDFs to the quantile functions, what we only need to do is do the inversion. That is the symmetry around the y equals x axis. So the CDF here is supported between 0 and 5 and 10 and it takes values between 0 and 1. The quantile is just simply the function that takes values between 0 and 10 and inputs between 0 and 1. And that's it. The only thing you need to do now to actually compute this Wasserstein distance is to integrate those differences and measure them and apply function C to each of those differences, absolute differences. And there is also a very simple link with the Monge map. The Monge map in here in this case has a closed form. So here I'm giving it for one direction, which is from nu to mu. I apologize, it should be, if you want to go from mu to nu, you should first compute on the right f mu and f minus 1 of nu on the left. And more generally, this works for any submodular cost, that is any function cost c, such that its derivatives with respect to x and y is strictly negative. And this was used in a lot of works recently to approximate optimal transfer for higher dimensions, not only for dimension 1, but for dimension d. And the idea that was put forward by Julien Rabin and co-authors in 2011 was, well, if it's so easy to compute optimal transport on univariate measures, let's just extract univariate measures from multivariate measures and repeatedly compute transport on those projections. And so you're going to sample a direction theta, project against theta both measures mu and nu, and compare their distributions, the distribution of those projections. And it's not related to, well, it is related certainly, but it's certainly not approximating optimal transport, that we know. But it's very easy to compute and very fast. And so this has found some applications. Now, this was the first easy case. There is another easy case out there for optimal transport. And this time it's a bit more restrictive because it builds on the squared Euclidean distance cost. And it applies for Gaussian measures. So notice that here omega is Rd. The result actually applies to Hilbert spaces as well. That is, dimension d goes to infinity. But for simplicity, let's just assume here that we're taking a finite dimensional Hilbert spaces or Euclidean spaces. So we have two measures. U is a Gaussian with mean m mu and covariance matrix sigma mu. Nu is another Gaussian. Then what we can show is that the Kantorovich problem, or the Monge problem that we described earlier, that move mass optimally between one Gaussian and another. So essentially it's as if you had two Gaussian mountains of sand in high dimensions and you want to move optimally from one to the other. Then the Wasserstein distance between them is basically the difference in the means of those Gaussians plus a discrepancy, actually a metric, between the covariances. So this splits very nicely between how different their means are and how different their covariances are. And the distance for covariances that is used is called the Burr's metric. So the Burr's metric is this object that takes a trace of the first covariance, a trace of the second covariance, and subtracts some kind of mixture of the two, which is this matrix made of square roots. A more interesting feature of this, and actually a way to prove it, is that one can show that the Monge map here to go from one Gaussian to the other is known and only depends on those covariances. And maybe a remark I haven't done is that here to compute the distance, this works even if the covariance matrices are degenerate. We never encounter a problem, for instance, if those covariances have some zero eigenvalues. This is not the case to compute the Monge map. The Monge map will only work here if the first covariance matrix is full dimensional. And I don't really have the time to explain this because the lecture is short, but let me say that the way you prove that this map is optimal is by noticing the following thing. First, you can actually do the computations by yourself and see that indeed this map transforms the first Gaussian into the second Gaussian. And this is just a very classic result resulting from the application of a linear map on the random variable that is Gaussian distributed. If a random variable is Gaussian distributed, then a linear or affine map of that random variable is also Gaussian, and we know how to derive its new mean and covariance matrix. So you can trust me that this map here which to x associates the measure of the mean of the target measure plus a linear map that's x minus the mean of the first measure, is going to map nu to nu. The second thing you should notice is that this map will necessarily be optimal. So it is such that T sharp mu is equal to nu, but it is optimal because of Brognier theorem. And the reason why is that if you look at this map, which takes values, points, for instance, in the first measure and brings them to a second measure, you can cast it exactly as the gradient of a convex function. So, I'm sorry, please assume the psi above here is an f. So you can write indeed that this map, this affine map, is the gradient of f, which is defined as a quadratic form. And what is nice about this quadratic form is that this is just an identity. This quadratic form is positive definite. It's just a bunch of left and right products of positive definite matrices and square roots, which all conserve positive definiteness. Therefore, the map T is the gradient of a quadratic convex function, a quadratic positive definite, therefore convex function, and it maps mu to nu, therefore it must be optimal. And here in this picture, we actually get to see what this potential looks like. We have a measure mu, the Gaussian on the left, and measure nu, the Gaussian on the right, and then in between, we have the map that transports it, and that map is the gradient of the quadratic function that is pictured above. This result applies more generally for so-called elliptically contoured distributions. So those are distributions that have contours. If you were to plot the contour plot of those distributions, they will all follow elliptic lines. So this doesn't mean that two elliptically contoured distributions can be transported in a closed form. It just means that if you take two distributions in the same elliptic family, then you can have the transport in closed form. And a very simple and nice application of this is between ellipsoids, for instance. Here I'm plotting various ellipsoids. The green ones are non-degenerate. They have matrices that have full rank. But for instance, B0 here is just one point with an ellipsoid that is 0. So it's a 0-size ellipsoid. B2 here is two-dimensional, whereas B1 is one-dimensional. It's just a segment. Well, it turns out that the Wasserstein distance between the upper left ellipsoid and all the other bodies is the same. This is actually a rendering of a 3D picture, and it's a real plot. Now, when we focus on the Wasserstein distance, usually we are going to use it on point clouds. And so let me start with the simplest of point clouds, that is single points. And defining an important characteristic of the Wasserstein distance between point clouds is that if you instantiate it between 2 points, that is one point cloud is just one Dirac and another is just another Dirac, you get that the distance between those two probability distributions is actually equal to the distance between the original points. In other words, if you define on a space omega some distance d, the distance between Diracs supported on 2 points is the same as the distance between the 2 points. And this is not a feature that you will see observed in most other metrics between probability distributions. So what you have a canonical lift of the base metric to define a metric between distributions. If you instantiate it now between 2 point clouds of the same size, so here two measures with discrete measures with n points and weights, probability weights 1 over n, then this problem reduces to the optimal matching problem, the optimal assignment problem. Here it's simple somewhat. One Barak only needs to go to one front line, and then you just need to find the best possible way to pair them. And this is, of course, easily formulated as a permutation problem from minimizing over the space of permutations, but it's solved as a variant of a linear programming problem, and the default algorithm for this would be to use the Hungarian algorithm. Now, if you are a bit more general and you do not assume that the number of points is the same all the time, we are going to introduce two discrete measures, mu and nu, that are supported on n and m points. In that setup, each measure is described by two things: locations, so here there would be xi and yj, those are locations on the map, and weights, ai and bj. And those two things for each measure are equally important here, and they will need to be considered to find out what is the optimal way of moving the mass on the left to the right. So if you go back to, this is really the Kantorovich problem, where the red crosses are barracks, they might be big or small, and the blue crosses are the front lines. But if you want to take a maybe more Pacific analogy, this might be, for instance, mines that produce some resource on the left, and factories that need that resource on the right. And you want to find a good way to truck around those resources. And the way you formulate this, and this should ring a bell if you go back to the Kantorovich problem that I described earlier, is on the one hand we are going to encapsulate entirely the geometry of the problem by forming a cost matrix mxy. And that cost matrix describes every distance between pairs of resource input locations and target location. So it will basically list all of the distance between xi's and yj's. So if you have n and m points respectively, mxy is going to be an n times m matrix. Now, this was the distance that I mentioned in the early slide about Kantorovich. The other thing that Kantorovich is interested in is all the set of admissible transportation plans. And here it's going to take the following form. It's going to be matrices P of size n times m, such that the row sums of those matrices are equal to A, whereas the column sums are equal to B. So as long as a matrix is such that its rows sum to A and columns sum to B, and it is made of non-negative elements, it is a valid transportation plan. And the optimal transport problem is just minimizing the total cost of transportation among those plans. One thing I haven't mentioned in the introduction is that one reason why Kantorovich is so famously associated with this problem is not so much because he wrote it, because as we mentioned, other people had considered before, Tolstoy and at the same time Hitchcock. The main reason is that he was the first to highlight an interesting alternative formulation for that problem, which is called the dual Kantorovich problem. So if you know a bit about convex optimization, you know that every convex problem has a dual, and essentially what the dual does is cast the original problem by switching the position of the constraint and the objective. So to be a bit more clear, in the problem above, we are minimizing over a space of matrices of size n times m, and the constraints are each defined as n constraints for the marginal A and m constraints for marginal B. So variables is nm, and constraints is basically n plus m. In the dual problem below, you see that I have introduced two optimization variables, and one is of size n and the other is of size m. So now instead of nm variables, we only have n plus m. However, interestingly, we have now nm constraints. For every I and j, I need that alpha I plus beta j is smaller than the distance between xi to yj. And you remember that a and b were in the original problem at the bottom in the constraint. Now they appear in the objective. So the dual is basically a way to flip, turn head over heels the optimization problem and put the constraints in the objective and the objective in the constraints. And in the optimal transport problem, this actually provides you a very intuitive result. It basically tells you, the dual variables are a way to tell you what are the locations in the transportation problems that seem to be the most costly when you're actually going to run the optimal transport problem. So I cannot give you a course on duality here, and I encourage you to actually dig into this fascinating topic. But the idea here is that I have plotted on the left the optimal transport. Those rays basically tell me how much mass I must carry from blues to the red. On the right, I'm plotting for every point the value of the dual variable that is associated with it. As I showed above, there is one dual variable alpha I for every input point I, and one variable beta j for every output value j. And what you see is that the dual variables are white, very high, according to my color map on the bottom left. That is among the input sources. And it's very red among the target sources, the target points at the upper right. So what this is basically telling you is that when you're doing the optimal transport, you're going to pay a big price to transport, either taking mass or resources from the two bottom left sources, or bringing it to the upper right target. And so, without going a bit further, what you can instantly see is that if you were to relocate, for instance, factories or mines so that the transport cost is a bit smaller, typically you would start by thinking about those upper left, lower left and upper right points. Now, the optimal transport problem is a linear program. Remember, P is linearly constrained. It has linear row sum and column sum constraints, non-negative constraints for each entry, and you're basically trying to minimize the dot product between the matrix and this matrix MXY. Getting there has basically mobilized the brightest minds in operations research for several years. And it turns out that the optimal transport problem is a classic mean cost flow problem. And the good news and the bad news at the same time is that this is relatively cheap as far as linear programs go, but it's very costly for large-scale applications because it's essentially cubic in the size. And this is, of course, a big problem in every field of engineering if you want to use optimal transport. There is another problem which to me is almost as important, and which is that if you are only considering the optimal transport value, the value of the Wasserstein distance, then you should be fine with this. But if you're actually considering differentiating the optimal transport problem, that is changing a little bit some of its parameters, it's well known that linear programs can be very unstable. And by this is basically translating the fact that the solution P star is not always unique. So here in this diagram, of course, it looks unique, but imagine I start playing with X, locations of the first measure, and I start wiggling with it. At some point, I might hit a facet of the polytope of transportation matrices, and all of a sudden, I'm left with an infinite number of optimal transports. And of course, in practice, this very rarely happens. But what happens is that I have gone from a situation where I had one very well specified and constant P star, no matter how I would wiggle, change a bit my values, to a different solution. So I jumped in a discontinuous manner from one solution to another. For a while, the solution was the same. It was stable at one corner, and all of a sudden it jumped to another corner. And that is basically the reason why the Wasserstein distance is not differentiable in its inputs. And please consider that here I've just illustrated this for changes in X. But of course, if I were to change the values of A or B, this would result in exactly the same type of pathology. And finally, and this is particularly important for people in our community in machine learning, the computation of the optimal transport problem is actually quite hard, and it requires solving it with network flow solvers. And they're not very well tailored for the current computational paradigms of high performance computing on parallel hardware, such as GPUs, etc. And to illustrate this, this is basically one of the simplest code you can find to compute to solve this network flow solver. This is not even a code that is inherited from a larger linear programming package. It's really something that was designed specifically for this. And this is already a few hundred lines. And if you were to use more optimized packages, there would be a few thousand of lines. And most of those operations are actually very sequential and iterative. And therefore, they are not well suited to parallelism. So basically, computations and trying to compute optimal transport in a classic linear programming way hits a few problems in the current computational environment. So this already suggests maybe there should be another way to compute optimal transport, or at least we should seek a different way. There is an even worse aspect of optimal transport that is especially impactful when you consider dimensions that are higher than 1 or 2. And let me explain exactly what I mean by this. In most of applications, our distributions mu and nu are continuous. So there are some applications where everything is discrete, but even if that size, the size of that discrete set is very large, it's common to think about what we observe as a sample of what is a continuous distribution, or a distribution taking values in a very large space. And what we have access to is just data. And we never have the full picture of what the measure looks like. And what I have basically presented so far is when those measures are not one-dimensional or they are not Gaussians, then we rely on samples to compute the Wasserstein distance. And essentially what we do is compute the Wasserstein distance between the samples, and hopefully this will approximate the Wasserstein distance between the original measures. So the first step is actually to compute things. And as I just told you, in the generic case, with arbitrary costs, the computation is pretty heavy. It's already cubic, so it's enough to actually scare most practitioners. The second problem that comes with using optimal transport in its linear programming formulation is what people call the statistical property or the statistical complexity of this approach. Essentially, it tries to understand what is the difference between the actual Wasserstein distance between two densities, which you will never have access to, but which we can try to study, and which we would ideally want to compute if we had access to infinite data, and the Wasserstein distance that you will be left computing between your samples. And statistically, what we want to know is, what is this? Is there a way to upper bound this quantity, the expectation in terms of samples, of the deviation between the Wasserstein distance between the true densities and the samples, as a function of n or m? And to just write in a slide a few negative results, it's very well known that the higher the dimension, the harder it will become to approximate the true Wasserstein distance. So here in the slide I'm putting the result for d bigger than 3, but it turns out that even for d equal to 2 or 3, you can observe that it's very difficult to approximate efficiently the Wasserstein distance between two measures if you rely on n samples. And that difficulty is illustrated by the rate, which rate here on the right, which is exponential. Basically, it says that to approximate this with high quality, you will need an exponential number of samples that grows exponentially with dimension to have a good approximation. And those results, as you can imagine, come in very different flavors depending on what is the p exponent that you're using, what is the assumption that you're making on the measures mu and nu. But overall, let me just say that the picture is pretty bleak. So there's two big roadblocks that should prevent you actually from using optimal transport, but it turns out that we still do. So how come? Well, in fact, it's simply because people in applications of optimal transport usually do not stop at the linear programming formulation. They have been doing what I would call a regularization of the optimal transport problem. And by regularization, I just mean that they take those LPs that were formulated 100 years ago, and or 80 years ago, and they simply start adding up more properties or requiring more regularity from the variables or simplifying the constraints. So for instance, if you look at the dual optimal transport problem, which is this generalization of the primal, this would be the same as restricting the space of dual variables. This works either in the continuous setting here, where I'm giving you the formulas for the continuous problem, or in the discrete one with the sup alpha and beta that I mentioned earlier. And so you can start thinking about adding more restrictions to the set of potentials, and here you get quite popular approach to approximate optimal transport recently, which is this so-called Wasserstein-Gunn approach, which builds on something called the Kantorovich duality, which says that the dual problem that Kantorovich studied, when the cost is a distance, can be solved by taking the supremum over all one Lipschitz functions of the integral of that function against the difference of measures. And it's closer to what we've been describing in the primal. Well, you could start thinking about throwing some restrictions on the cost by saying the cost is thresholded. That simplifies things. Or that the cost has a very specific structure. It is the shortest path metric on a graph, for instance. You could say that, well, whenever you give me measures mu and u, I might try to simplify them. So the first thing you could do, for instance, is compute k-means. This reduces substantially the number of points, but also seems to make sense statistically. You could project, as I mentioned earlier, on lines or even subspaces, and this is a recent line of work. And finally, and this is what I'm going to present in the last minutes of this lecture, and which has generated quite a lot of applications, you could add a prior on the coupling itself. That is, require something more from the coupling, not just ask that it conserves the mass and it is non-negative. And geometrically, what it basically boils down to is to aim for a transportation matrix P that is not necessarily right at the optimum, but is a bit more in the middle, as long as you can get there faster, in a more scalable manner, using simpler algorithms than network flow solvers. And all of this is achieved by using this so-called entropic regularization. And let me say that this idea dates back to economists, actually, in the 60s, who were trying to use the solutions of linear programs to model actual transportation of people in routes, in transportation networks, and found it very frustrating to use those models because they were very unstable with respect to the inputs and other issues. And so they threw in some regularization. So what is this entropic regularization about? Well, it's simply the idea of taking the original optimal transport problem, which I have written again here in the middle, and adding this minus gamma entropy of P. So the entropy is a natural function to consider for a coupling P. P is itself, remember, sums to 1. All of the rows sums to A, therefore all of its entries sum to 1. And the advantage of the entropy is that it is a concave, actually a strongly concave function on the simplex. So if you actually put minus gamma, the entropy of P, right next to your objective, you get that you're now solving a gamma strongly convex problem. So that means that when I am going to look for a P there, that it minimizes this, there's only one that does so, because of this strong convexity. Now, what does this mean intuitively to add in entropy, or neg entropy? Well, the first thing you should notice is the following. When I am computing transport between two measures, here, for instance, those two univariate ones, if I solve the LP, what I get is this very thin matrix. Or basically here mu is discretized as 100, histogram of size 100, nu size 100. So the coupling will be a matrix of size 100 times 100, 10,000 potentially useful variables. It turns out that because we are solving a linear program, when there is no regularization, you cannot have more non-zero variables than the number of constraints. This is a golden rule for linear programs. Therefore, when you solve this LP that I described earlier, you will find matrices that are solutions that have 10,000 variables, but only 200 that are non-zero. And actually, this really looks a lot like the Monge problem. So this is one of the regimes where if you discretize small enough, your problem becomes somewhat a Monge-like problem. Now, if you start considering regularization strengths which are strictly positive, then this means that you want more entropy from the coupling. And remember, entropy is basically something that encourages you to be diffuse. But one of the important things here is that we cannot get to something that is just more blurred directly by blurring the line on the left. Because if we do so, we will start violating the conservation of mass constraint. We don't want to blur in areas where we cannot create mass. So we have this very specific, strange blur that kind of blurs things when you don't really care in terms of cost, but doesn't blur anything when actually you're not allowed to transport more than you can. And when you start increasing the strength of this regularization, you just get to the product of the marginals that we've mentioned before. So why is this regularization useful and actually nice and well suited to the current computational environment? Well, it's because if you just use the Lagrange method of multipliers on this convex problem, it's a textbook, very simple convex problem that you can solve, then you get that the solution must have a very specific form. It has a very nice factorized form. And the factorization is as following. If P gamma is indeed the solution to this problem, then P gamma must be such that it is a diagonal matrix times K times diagonal matrix, where K is something that is actually given to me by the problem. It's just exponential minus the cost matrix. And this is why I'm coloring it in red and blue. It's something that basically merges all of the geometry between the first and the second measure. And the reason I'm calling it K is also because it's clearly a kernel. And the way you get there is just, again, by just applying Lagrange method of multipliers. Just write the objective, you add Lagrange multiplier for each equality constraint, take derivatives, and then you will see that this solution has this factorization. Now, once you know that, typically in optimization, we are going to use the fact that this must have a certain, those values u and v's are not anything. They must be such that this matrix satisfies the row marginal constraints and the column constraints. So let us walk a bit through this. Well, the first thing you should realize when you see this equation is that, so you have this matrix, diagonal k diagonal times 1 equals A, diagonal k transpose diagonal times 1 equals B. Well, the first thing is diagonal matrix times 1 is just the value of the vector itself. So this can go away. Now, a diagonal matrix times kv, or k transpose u here, it's just basically the element-wise product of two vectors. So you have that ukv, element-wise, vk transpose u are equal to A and B respectively. And if this is just element-wise products, you can also use element-wise divisions to basically say that you are looking for two vectors u and v that satisfy this nonlinear equation. It's nonlinear because v appears in the denominator of the first one and u appears in the denominator of the second one. Now, the very naive approach to solve this would be to apply the first update, start with a v, apply the first update, and then get u, and then get a new v by applying the second update. Basically, you just want those two things to validate those equations, so you just do a fixed point iteration. And that works. Sinkhorn proved that it worked in the 60s, and this was better understood in the 80s, and more recently, because this has become a prominent solver for optimal transport, there's been a lot of very nice works that actually quantify better the convergence of this algorithm and the convergence of what you get respective to the actual optimal transport problem. The first thing you should notice, and the most important one, is that this algorithm is now quadratic. Instead of being cubic, we are essentially just simply multiplying a matrix, kernel matrix times a vector, so this is quadratic time, and then just doing element-wise divisions of vectors, and this is extremely cheap. And not only that, in some settings that are relevant to graphics, either when you're using meshes or regular grids, it's well known that multiplying by a kernel is actually the same thing as doing some form of convolution. And so if it's a regular space, gridded space is just a regular Gaussian blur if you're using a square Euclidean distance, and if the distance is separable. And if you're using something a bit more clever, a setup where you're computing, comparing histograms on meshes, then you can use an approximation using the hit kernel. So this approach is provably convergent. It will blow up in the case where gamma is very small. There's no free lunch. But there have been a lot of follow-up works that show that this actually can be stabilized numerically and works better, even in low-dimensional setting, than the linear programming formulation, granted that you could even compute the linear programming formulation. Now, to close the lecture, I would like to highlight a very important reason why this algorithm is actually actively used both in machine learning and in graphics. The first thing is the following. When you want to compute the Wasserstein distance, it's no longer enough, as I mentioned in the introduction, to simply compute it. What you want to be able to do is maybe to minimize it with respect to 1 or 2 parameters here. And those parameters might be, for instance, the weights. So you want to be able to know what happens if I change a little bit the weights of my the red measure, or equivalently, what happens if I change the location of my red measure. And what I need to know is a simple algorithm to get access to this gradient. And in most of the current deep learning pipelines, both A or X might be themselves the output of a neural network. So I need to have access to something that is easy to integrate in an end-to-end learning architecture. And the reason why the synchron algorithm is very simple to use in that context is that without thinking further about it, you can simply see it as a program that takes in all of the parameters mu and u, so the cost, etc., and simply runs an iterative algorithm for a few iterations by doing those synchron steps. And then we know that using PyTorch, TensorFlow, JAX, AutoGrad, whatever the framework you prefer, you can actually have access in the same complexity to the gradients of the Wasserstein distance with respect to any parameter. So this is a bit like saying that the synchron algorithm looks like a stacked neural network where all of the layers, the multiplication by a matrix is done with respect to k, which depends on your inputs, and it's the same across all layers. And the nonlinearities is this division, element-wise division of the output and multiplication by a or b. Now it's very easy to just simply backpropagate the result that you got according to anything that you want. This could be a parameter for the cost, this could be the weights, or etc., etc. And we've been using this repeatedly in recent years. So the first application of this was with a paper at SIGGRAPH with Nicolas Bonil, and we have had some very interesting follow-up work with Mathieu Heitz in a recent journal paper. So with this, I will close my presentation. I will leave some applications in the slides for you to check if you want. And I look forward to your questions. Thank you very much.